All right, so question number 6 asks you to write the balanced reaction equations for glycolysis and gluconeogenesis, and then asks as a follow-up, how is gluconeogenesis able to occur when the conversion of glucose to pyruvate is energetically downhill? All right, so let's write these two equations. We'll start with glycolysis. All right, so we're taking glucose, right, and we have we're going to get ATP out of this, a net of ATP, and it turns out we actually get 2 ATPs. So we have to add in our reactants to make the ATP. So we have 2 ADPs and 2 phosphates. And we also end up getting 2 NADHs out as products. So we have 2 NAD pluses here as reactants. And the products then that we end up getting are, we get 2 pyruvates, we get 2 ATPs, sorry, got the 2 on there, 2 ATPs, 2 NADHs, and and we end up also getting this part over here, the protons and the water molecules that we get out. I don't really care if you know about those parts, but the other portions of this you should know. So basically glycolysis, we take a single glucose and we generate 2 ATPs and 2 NADHs out of that, and the glucose actually becomes 2 pyruvate molecules. Now, for gluconeogenesis, right, we're going to do this in reverse order, but we're going to do it slightly differently. So we're going to start with 2 pyruvates, and we're going to go towards 1 glucose. So the carbon portion of this is going to be the same. Now the difference is what we're having to put in. So if we did this just in exact opposite order, we would put in just 2 ATPs here and cleave them, giving us 2 ADPs and 2 phosphates. But because we have extra ATP that is used by pyruvate carboxylase, all right, and then we're also not generating any ATP because we're bypassing the PFK and hexokinase steps. We actually end up in the net reaction here using more ATPs. So we actually end up using 4 ATPs. And then we also use some GTPs as well. All right, so we've got that. All there is energy that we're putting into the system. And we're still going to use the NADHs. And then if you wanted to throw in here the water and the protons. All right, these are all reactants for gluconeogenesis, right? The products then we get are glucose, we get 4 ADPs and we get 2 GDPs, get a total of 6 phosphates, and 2 NAD pluses. All right, so that is, this down here then is a balanced reaction for gluconeogenesis. Now, the follow-up part of this question, how is gluconeogenesis able to occur when the conversion of glucose to pyruvate is energetically downhill? So this reaction up here has a delta G that is less than 0. All right. Normally, if we just flipped the reaction around, the delta G sign would just change, which would mean that the delta G, that gluconeogenesis would be thermodynamically uphill if we tried to do it in the same way. But what we do instead is we are using extra energy here in the form of extra ATPs and these extra GTPs that are not present in glycolysis. And so as a result, there's now more energy being put into the reverse reaction of gluconeogenesis, which allows it to also be thermodynamically favorable. And this is also part of the reason why opposing pathways and metabolism have to be different, because both of the opposing pathways have to be thermodynamically downhill, and that's not possible unless you add energy into extra energy into one of the two pathways. And that's it for number 6.